Just to.
I am not. Oh, I thought you wanted to do it after. Either way. Sure.
Oh, yeah, sure.
Okay, so I'm going to take you 15 minutes.
Yeah.
That's fine, then we have time to do it. Okay.
Well, welcome everybody. It's a great pleasure to have this workshop on, I'm not sure I remember the title, model theory, dynamics, differential algebraic methods, or something like that altogether. Anyway, so welcome to the Fields Institute for Research in the Mathematical Sciences. My name is Deirdre Haskell and I'm the director of the Institute. And the Institute exists to promote, make opportunities for research in mathematics understood in the broadest possible sense. And so we have, we make events happen to bring people together in order to make opportunities for research to happen in lots of different ways. And it's a great pleasure for me to welcome this particular group here today and for this week. Let's see, I'm supposed to say that we are here, we work on the traditional lands of the Huron-Wendat, the Seneca, and the Mississauga of the Credit. And many people from across Turtle Island still work on this land, and it's a privilege to be able to do our work here. There's a lot of things I'm supposed to say, and I'm trying to remember what they all are. So we are funded by the Ministry of Colleges, Universities, Research Excellence and Security of the Province of Ontario, by the Natural Sciences and Engineering Research Council of the federal government, by the National Science Foundation of the United States, and by a network of 9 principal sponsoring universities from across Ontario, and a growing network of affiliate universities across Canada and across the world. And if you want to discuss with your department whether you might become an affiliate university of the Fields Institute, then that would be a really great contribution. So we're here this week for this conference in model theory. And one of the events on Wednesday, we're especially remembering our friend and colleague Zoe Chatsidakis. There will be a party at my house here in Toronto on the Wednesday evening. And so please sign up on a RSVP sheet, which I'll put out on the main desk to let me know how many people are likely to be there and to keep track. So with that, I think we can move on to actually starting this morning's session. And I will hand over to Jason, who will be running the session. Oh, actually, let me add, we should remember to use the microphone in case we have any online participants. We don't have any right now, but just if there are some. And the speaker will be wearing a microphone as well. Yeah, please, when you ask questions, then remember to use the microphone. There are online participants that should be waiting until.
Yeah, looks like there are some.
Oh, there are some, so we should wait.
Yeah, we're gonna wait till 9:30.
Get another cup of coffee. Is there coffee on?
We're preparing.
Yeah, we have lots of time.
Yeah, wow, I should have made the remarks at 9:26 or something.
Yeah, right,
like
who
that.
knew that it would be so short? And it usually takes a conversation session.
Golden roast. in there.
Yeah, so it's interesting something.
I mean, please will be in a friend.
Just for that.
Things are going well. Yeah, it's, pretty much. I mean, I'm doing a sabbatical in the fall, but sometimes that goes into some admin thing, but I can't get out. I did say no, and then I said, well, you could do this before your status starts, and then it just goes over. It's just, it doesn't seem like it's that much, but it's like I'm supposed to share the books, but I get all this. Yes, but I'm supposed to contact friends and groups. Get hotels. I mean, it's not like it's that much, but it's just like, I don't know, somehow I'm going to just go with all. You have a slide? Oh, nice. But you don't, you not do it? Probably get to choose what you want. Yeah. Well, you're like Jamie coordinated or something? Oh. It's yeah, teaching. I was teaching. I got asked to teach differential geometry, and I don't really know this at all. I did learn it. I did teach it. It was one of, yeah. I was posting. And then I'm teaching complex analysis. I haven't taught it before. I think it's 30. I don't know. I haven't touched it since I was a student. It's only analysis that I thought was going to be too good. I hope this is not a hot mic.
Jason tells the world analysis is an Let's look at the appearance of your colleagues next. Who's real?
Oh, yeah, that's great. But it's not, you can't be terrified anymore. Like, even if you give a bad talk, it's like, yeah. I guess I feel like, yeah, I don't want to give a bad talk, but if I do, yeah.
And that's how it's.
Oh, wow. You made the right choice. Sure. Can you imagine being huh?
Yes, no, that's true.
Just if she doesn't know what she wants to study.
Maybe you.
And what about Madeline? She's she would be a tattoo artist. Yeah. But she's like, she's happy. She put a tattoo. Because at some point, like when she was young, she wanted to do robotics.
Yeah.
But she's probably like very good at it.
Oh, yeah.
Uh-huh.
It's everything like full.
I
Can
don't
you
think
imagine being friends with a rapper? No, I can't. Can she parlay that into like some personal life?
Right. So after we thought about it.
Yeah, that's true. Huh. And what about Felix? He wants he's into software. Okay. Yeah. I told him. Shut up. Yeah, Chris is like 6'1" or something. No, he has no shortage. You don't need a paternity
Just like.
That's a good question.
It just occurred to me that
I guess we're using this as the clock. It's a little slow. That's true. Just need to keep it simple.
oh, there's no way to overdo it.
Your laptop? Yeah, I can.
Was that one, open this one?
Maybe it doesn't matter. You can see the screen.
Yeah.
Okay, I watched this my turn.
Okay. Okay, welcome to this meeting at the Fields Institute. So our first speaker is Laura DeMarco from Harvard University, speaking about periodic points, torsion points, and bifurcations.
Okay, thank you. Is my microphone on? Is that working? Nobody knows. You can hear me, but I don't know if anyone on the. All right, well, I'll just talk and, oh, okay, Shane says we can hear you. All right, great. But then do we need to remove that from the, or does it go away by itself? There we go. Okay, anyways, thank you. Thank you for the invitation. Thanks, everybody. It's really a pleasure to be here and to start this event off. I'm going to give a talk about a result in complex dynamics, but I chose a topic that I'm hoping will connect to a lot of the themes that will be discussed at this conference. Periodic points, torsion points, and bifurcations, the latter specifically being the complex dynamics. And hopefully I'll be able to tell you what this picture is at the end of the talk. I don't know if you can see, of course, there's a Mandelbrot set here, but the interesting part to me is the stuff that's all around it, all of these swirls and circle things, loops that surround it. Anyways, when we think of complex dynamics, at least in dimension one, we often think of pictures of this sort. These are illustrating what are called Julia sets associated to a few examples of quadratic polynomials. So we're interested in the dynamics of holomorphic self-maps from the Riemann sphere to itself, or the projective line to itself, defined over the field of complex numbers. And in dynamics, we study the iteration of these maps, namely the compositions of F with itself, as n goes to infinity, and try to understand the behavior of this sequence of functions. Of course, very, very simple formulas give rise to very interesting pictures. I've just put the picture associated to the quadratic polynomial z squared plus I here, z squared minus 1 over on the other side. We typically break our space into two parts where the dynamics are relatively easy to understand, what we call a Fatou set, which is where we have nice dynamics, or the Julia set, where we have chaotic dynamics. I'll not go through the formal definition, because what I want to talk about is a question that I've been thinking about for a very long time, and that a number of you have seen me give talks about probably several times over the last 10 years, which is related to the structure or the geometry of the set of points which are periodic or pre-periodic for a given dynamical system. So you fix one such function, okay, that's holomorphic from the Riemann sphere to itself. It's either a polynomial or a rational function of one variable. So you fix one and you look at all the points which have a finite orbit. That is, under iteration, the points will eventually cycle. So maybe they come back to themselves, or maybe they land on some periodic cycle. So this is some infinite, as soon as the degree is bigger than 1, this is some infinite subset of the sphere, and the geometry of that set is very complicated. The points are dense in this fractal shape. So the questions are roughly, to what extent does this set determine the dynamical system? Or to what extent does, say, some finite subset of this set determine the dynamical system? And another way to formulate that is, if you have, say, two maps, F and G, what can we say about the intersection of those two sets? And if that intersection is large, can you conclude that F and G are somehow the same or somehow related? Which, in fact, you can, and that's what this talk is about. So how large can that intersection even be? So this type of question, trying to understand the geometry of the set of periodic points or pre-periodic points has a long history, and people have been studying this for a long time. So I just put, for example, the work, so I mentioned the Fatou set and the Julia set. That decomposition of the sphere is named after these mathematicians, whose work was sort of building on the work of Montel, and was prompted by a competition problem that was announced in the early 1900s, specifically in 1915. And so a lot of that initial work was on how do we understand the global dynamics on the Riemann sphere, not just the local behavior, but it was focused on providing some kind of global theory for this class of dynamical systems. But I actually want to talk about another piece of work that was prompted by that same competition problem, which was the contribution of Samuel Lattès, who contributed a manuscript for this competition. He did not win. He was the runner-up. And he died in 1918, which was the year the competition closed. And so that was, I guess, the end of his work. But I want to say a little bit about what Lattès did, because it was what he did which has led, which in part is really what led me to be interested in this question very specifically. So I want to tell you about his work and how it's related to what what I've been thinking about recently. Okay, so what did Lattès do? So in this paper, which was published in 1918, Lattès was studying functional equations, so certain composition relations for these particular types of functions. So he was specifically interested in compositions with the Weierstrass P function, the doubly meromorphic, a doubly periodic meromorphic function on the plane associated to some lattice, lambda, in the plane. So I've drawn here my P function going down, and he wanted to know, when do you have rational functions f that are quotients of a linear function on the complex plane? So this composition, what functions f and L or lattices lambda will make this diagram commute? Now, just a remark, the study of functional equations of this sort, namely composition relations, was something of interest at the time. In fact, there were a number of mathematicians that were thinking about various composition relations. So for example, just a few years later, Joseph Ritt completely resolved really the study of composition relations in the setting of polynomial functions of one variable. So polynomials of one variable, in the work of Ritt, he sorted out, when can you have a polynomial that can be decomposed as the composition of two others, or indeed decomposed perhaps in two different ways? What are the possibilities? So his work was completed in the 1920s. But I will remark that this has also been studied in other settings. The setting of rational functions, where f, g, h, q might be a rational function of one variable, is still not fully sorted. So a complete classification of composition relations of this sort in the setting of rational functions of one variable is still work in progress. And a number of people have been working on it, and a lot is known. A lot more is known now than 100 years ago, but it's still not completely resolved. Anyways, this work of Lattès, I want to put this in a picture to illustrate that this is really a dynamical relation. Namely, we can think of sort of the linear function as a dynamical system on the complex plane. Now, in order for this diagram to commute, it induces a dynamical system on the quotient of C by that lattice, namely the associated torus or elliptic curve, which I've drawn with a little point there to emphasize it's really an elliptic curve with a 0 for the group. So this linear function induces an endomorphism of that elliptic curve. And if such an F exists, so if you have such a triple, the lattice, the L, the F, you get what we now call a Lattès map. So there's a class of examples that Lattès was interested in, and these induce these rational functions, which you can think of as dynamical system on the Riemann sphere. Of course, notice that the P function here, of course, factors through that elliptic curve, and then the quotient from the torus down to the Riemann sphere is a degree 2 quotient that just identifies a point with its group inverse. Right. So what was Lattès looking at? Oh, I forgot I have this slide. So by the way, this is not just an abstract consideration. So once you know you can do this, and in fact you can do this for any lattice, you can even build explicit formulas. So it's not just abstract nonsense. You can write down formulas. Here is a function which realizes this. So for example, if you take the square lattice that I've depicted here as your lambda, and take, for example, the multiplication by 2 linear function on C, which induces the multiplication by 2 endomorphism on the associated square torus. This is an example formula that you can get. You can choose coordinates on your Riemann sphere and write down the formula. Okay. And by the way, there's this really great reference by Jack Milner, who has a whole article on the history of these things and goes in depth on these examples. And I do recommend, if you're interested in reading more, taking a look at this article that Milner wrote. Anyhow, so what did Lattès do? So let's focus on that example. That particular example from my previous slide is in Lattès's 1918 paper. He worked out that example explicitly. So if you take that one, so as I said, the linear function, which is adding a point to itself, or in other words, multiplication by 2, a very elementary observation, which is contained in Latez's work, is that the torsion points, well, it's not quite phrased this way, but is that the torsion points on the elliptic curve, namely the points that have finite order for the group structure, correspond under the projection to the periodic or pre-periodic points for the associated dynamical system. So a point is torsion up here if and only if, under iteration of f, it has a finite orbit on P1. So this is quite easy to check. But in particular, what did it imply? It implied that these dynamical systems that you get down on the Riemann sphere are everywhere chaotic in some precise sense. In particular, these periodic and pre-periodic points are, oh, I forgot I had drawn these pictures. Let me get to the conclusion and then I'll come back. So these periodic and pre-periodic points are in fact dense in the Riemann sphere for this class of examples, which is very different from iterating a polynomial function. If you take those examples, the pictures I showed you on the earlier slide, z squared minus 1, if that's your function, there are always lots of points that under iteration go to infinity for a polynomial. So the periodic points are trapped in some fractal subset of the sphere. But in this class of examples, the periodic and the pre-periodic points are in fact dense on the Riemann sphere. So this polka dot picture is just to illustrate the torsion points on the elliptic curve projecting down to the pre-periodic points on the Riemann sphere. So you have this dense set of points that are pre-periodic. So in particular, what we now call the Julia set, though of course it wasn't called that in 1918, what we now call the Julia set is the entire Riemann sphere for this example. So you don't get pretty fractal pictures by studying these examples, but you do get something different, something that was surprising at the time and interesting. But from a dynamical point of view, maybe they're not so interesting. After all, the dynamics is linear. I mean, it came from, in this case, multiplication by 2, or there could be some other, in fact, you can always take an endomorphism of an elliptic curve and pass to the quotient, and you'll get an associated Latez map with the same property, this polka dot picture of periodic points. There's no interesting fractal that we're seeing. From a dynamical point of view, maybe very boring. And so in some ways, this work was kind of forgotten. Great, there's an example, but so what? Like, why is that interesting? So maybe that's why Latez did not win that particular competition in 1918. Julia was the winner, by the way. Fatou did not submit his manuscript. But there's an interesting story there. Okay, so I want to now jump ahead 100 years later to one way in which this class of examples that Latez introduced us to and that are called Latez examples or Latez maps, how they've turned out to be quite useful and actually very interesting, that have led to some new questions about more general dynamical systems. I want to share with you a problem that I had been thinking about for a number of years, which is really a question that was brought up first in an article of Bogomolov and Schinkel, and revisited 10 years later in a formal conjecture that I will tell you in a moment. But the question roughly is the following. Suppose you now have two elliptic curves, E1 and E2. Again, everything is over the field of complex numbers. And consider these associated projections that I was mentioning before. And the question is, sort of how large, or their question was, how large is the overlap of the projection of the torsion points from the first elliptic curve with the projection of the torsion points from the second? How large can that be? Okay, and so the picture you should have in mind is that I have my blue polka dot picture here and my red polka dot picture on the other side, and I'm projecting each of them down to the Riemann sphere. Okay, so I have these two dense sets that have some sort of overlap. And what kind of overlap can they possibly have? Now, it turns out that it's actually well known at this stage that that intersection is usually finite. That intersection is usually finite. And Bogomolov and Schinkel at the time observed that as a consequence of Raynaud's theorem that resolved what's called the Manin-Mumford conjecture, one can prove quite easily it's a sort of an immediate corollary of their statement, that this intersection is finite. By the way, if you're familiar with this statement, which I have not put here on the slide, one works in the product E1 cross E2, a product P1 cross P1, you take the diagonal in P1 cross P1 and lift it up via the product of the projections, and you get a curve of genus bigger than 1, genus 2, 3, 4, or 5, depending on those projections. Anyways, and you're looking at the torsion points inside that curve. Anyhow, so what I want to emphasize is just as a consequence of the Monty-Mumford conjecture, they observed that unless these elliptic curves are the same elliptic curve with the same projection up to some obvious symmetries, this intersection has to be finite. Okay? And they were exploring, features of this intersection that might, say, pin down the elliptic curve uniquely. What can we say about if you just look at some particular subset of torsion points, what can you conclude about the associated elliptic curve? And so in particular, if two different ones have that same subset, are they necessarily isomorphic with the same projection? And those who are familiar with this statement might recognize that, of course, I've formulated it in complex geometry, but of course the proof is, the proofs are, there are many proofs now, but the proof is arithmetic in this, in his proof at least, Reynaud's proof. And so there's some sort of underlying arithmetic interest, which is what they were looking at in their paper. By the way, in fact, since this is a conference of model theorists, as well as dynamicists and algebraists and other, I should remark that since 1983, now again, I haven't stated the full Monty-Mumford conjecture and Reynaud theorem, but just a remark that since then, there have been many proofs of that same statement. It's a statement about a billion varieties and the geometry of subvarieties of a billion varieties and how they interact with the torsion points. There have been many proofs, and you might recognize from those names, if you can see them in the small print, that there are a number of different methods that go into proving it, in particular connections with model theory. So it's one of the reasons I wanted to emphasize here that there are a lot of different proofs of this type of statement. In particular, all of them imply that this intersection is finite. Okay, so there are some interesting connections with the themes of this conference. By the way, the finiteness in this case can also be proved using some dynamical input, but we don't know how to prove the full Monty-Mumford conjecture just from dynamical methods. What was I going to say? Ah, yes. Okay, we don't. Okay, so I see. So I don't really know how to answer this question, by the way. How large is that overlap? We don't know how big this intersection can actually be between two different elliptic curves, but the conjecture that was posed in this article from 2017 of Bogomolov, Fu, and Schinkel was that there should be a uniform bound over all pairs of elliptic curves, over all possible projections down to P1. There should be a uniform bound on how large the intersection of these two sets can be. Maybe they're no bigger, that there can be no more than 100 points in common or something. Okay, so we don't know how big they can be, but that the conjecture was that there would be a uniform bound. And indeed, this conjecture has been resolved, also via a number of different methods and a number of different proofs now. I mentioned some of the results. So Poineau was working specifically on this problem and gave a complete a complete statement. I am emphasizing the complete because I had worked on it prior, but we were not able to do the full statement. But now there's a number of different approaches to this problem and using a number of different methods. But the statement here is that indeed there is a uniform bound, let's say M, so that either this intersection is no bigger than M, or they had to have been the same elliptic curve in the first place, equipped with the same projection. By the way, this is in complex geometry, just to emphasize, of course, you have a one parameter family of elliptic curves. But in terms of pairs of elliptic curves and possible projections, you have a 5-dimensional space of possibilities. So this is a 5-parameter family of configurations of genuinely different, like a 5-dimensional moduli space of possible configurations here. In the work that I had done with Krieger and Yi, at the time we we handled like a two-dimensional subfamily of them, but now it's fully resolved from a number of different methods. By the way, another remark, just again, tying in with some model theory considerations, there was a nice article of Tom Scanlon from about 20 years ago called Automatic Uniformity, where he was looking in the setting of the Manning-Mumford conjecture and related statements. There are uniform versions of certain statements that are, as he calls them, automatic, that from my perspective just involves some sort of model theory magic that I don't understand, but there's some context in which you sort of automatically get uniform statements. Unfortunately, that does not hold in this setting where you're varying the geometry of the ambient space. So you do not get automatic uniformity in that sense, but uniformity still holds. But there, as I said, a number of proofs that involve a number of different types of techniques combining the algebra properties of the abelian varieties or the group structure or the dynamics. Oh, by the way, I wanted to emphasize, so how large can this intersection be? We don't know. I said we don't know the answer to that question. The current record holder appeared in a 2021 preprint of Fu and Stoll, where they've built explicit examples, an explicit example of pair where that intersection is exactly size 34, and that may very well be as large as it can be. There's no larger example, no. The current record. Okay, so going back to the dynamics and the complex dynamics, remember that these polka dot points here are exactly the sets of pre-periodic points associated to some dynamical system. So for example, you can take, again, as I did before, the multiplication by 2 endomorphism on each of the individual elliptic curves. They induce rational functions, f and g, down on P1. And what we're looking at here is the intersection of the pre-periodic points from 2 different transformations. So going back to my original question, how was related to the structure of this pre-periodic point set in general. So not just for lattice maps, but for any dynamical system, really, whether on P1 or on another space. But here I'm focused on the Riemann sphere. I'm focused on dimension 1. Okay. So of course, one can then ask, so it's maybe slightly more formally to the question I asked before, slightly, I'm not asking how large, but how large is this intersection between, if you're given now any non-trivial dynamical system on the Riemann sphere, by which I mean a rational function, f and g, each of which has degree bigger than 1. So not the Mobius transformations, because those are easy to analyze, and not constant functions. Those are also easy to analyze. So as soon as the degree is at least 2, you have non-trivial chaotic dynamics. How large can this intersection be? And the intersection being finite, in the same way that the finiteness was known from the Manning-Mumford conjecture, from Brayneau's theorem, we also know finiteness in the dynamical setting. And in fact, for the maps that are defined over Q bar, so they're algebraic, this was addressed in the thesis of Mimar in the late 1990s, but we also know the intersection is finite in the complex case, as long as the 2 maps are not compositionally related to one another. So that's also known. We also know finiteness in that case, not just over Q bar, over C as well, unless the sets are equal. So just going back to those same pictures I showed you at the beginning. Now remember, of course, to try to address this question going beyond elliptic curves and thinking about the dynamics of these maps, these sets in general are very complicated. Okay, so the pre-periodic points are dense in this Cantor set here in this picture, or dense in the boundary, the fractal boundary of that set. So in those Julia sets there. And so to envision how these intersect, what are we looking at? We're looking at these intersections of these complicated fractal sets. So by necessity, we have to do something that's different than what we did for the lattice maps, because the study in the lattice case was really exploiting, in fact, all the proofs, I should say, in the lattice setting, really exploit either the group structure itself or the fact that the dynamics is linear, that makes certain things actually quite a bit easier. But now we lose that linearity. We lose that linearity. Okay. However, we can, in fact, we can't say exactly how big this intersection can be, but sort of parallel to what we know in the case of lattice maps, we are now just recently, like 2 months ago, Mirito and I were able to fully resolve this particular question to show that if you bound the degrees of the maps, that indeed there is a uniform bound on the size of the intersection of these sets of pre-periodic points. So the statement is there is a uniform bound M, depending on your degree bound, so that either the intersection is no bigger than M or the sets are the same. The pre-periodic sets are the same. And by the way, it's known, so this is from complex dynamics methods, it's known, well, complex dynamics plus some arithmetic methods. Sorry, I was about to say something that was a lie. Okay, but it's known, anyways, it is known that if these sets are the same, then the two maps have the same measures of maximal entropy, and one can deduce from that that they satisfy a composition relation. So going back to some work of Levin and Pshititsky in complex dynamics. Okay, so this equality implies that the two maps are related, that some iterate of F and some iterate of G satisfies some relation up to some symmetry of the Julia set. Okay, I'm not going to be more precise than that, but there are some sort of composition relations that are satisfied as a consequence of this. In fact, maybe Tom, in your talk, aren't you going to be talking about composition relations between about iterates? So okay, so great. So I won't say anything more about composition relations because there's going to be a whole talk on it. So in any case, so this setting is essentially understood, up to a complete classification of what those relations are. And this is sort of a relatively small subset of pairs of maps. And so this is what we were really going for, is to say, even though we have this very complicated geometry and two Julia sets can look very similar, there can be a lot of overlap between two different fractals. But nevertheless, if you bound the degree of the maps, you're uniformly bounding the number of these common points. And so I want to say a little bit about what goes into a proof. There were some partial results that were known that I'm mentioning here of going past the linear case, past the group setting into this more general dynamical setting, which I really care about, and what methods from complex dynamics we've been using. So I want to say a little bit about that, because for me, it was the methods from the complex side that I find really interesting, and I'm hoping have other applications, or the statements themselves or the techniques we were using have led us to think about a lot of follow-up questions in complex dynamics that I find interesting. So I want to just inform you a little bit about what kind of math are we really doing here? What was missing from the partial results to go to this statement? Now, in a nutshell, it was to use a theory of stability from complex dynamics. So I'll tell you a little bit about what that is. Combined with some arithmetic techniques. It is not a purely complex analytic proof to deduce this. We don't know how to prove something like this just using complex analytic techniques, but we use complex dynamics and complex tools as input to a machine that involves equidistribution, arithmetic intersection theory, and a number of other tools. So it's a combination of tools, but I want to focus now on the complex part. So let's see, what time is it? It's 10 o'clock. Okay. So let me say a little bit about the tools. By the way, it also gives yet another proof or another input to the various proofs in the case of the elliptic curves, the lattice setting, the linear setting. Okay. So let me say a little bit about this, and hopefully I'll be able to say what the newest piece was from this spring, because I think, given there's at least one person here, and more than one indeed, who are from complex dynamics, I hope to say something about what I was finding most interesting. Okay, so let me just tell you a little bit about complex dynamics and the concept of stability. So the setting here, it's not written out in words, but it's depicted in this picture. So X here should be a parameter space. So I'm imagining I have a family of maps from P1 to P1, a family of rational functions, depending on some parameter lambda. Okay, X is a complex manifold. In fact, very specifically, it's algebraic, so a complex algebraic curve. Say, let's keep it one-dimensional for simplicity. And I have a family where you imagine these are all rational functions, and the coefficients are, say, meromorphic functions on some Riemann surface. Okay, so that's the setting. Here's my parameter space, and this picture represents the parameter space crossed with the dynamical space. So vertically, I have my Riemann sphere. So on each fiber there's a projection down to the base, and on each fiber of that projection, you have the associated action of the dynamical system. Now, these curves here drawn are representing sort of graphs over this parameter space of periodic points. Periodic points. Now, stability in dynamical systems, broadly speaking, means that if you start with a given dynamical system, one asks the question, to what extent does it change under perturbation? So if you perturb the map itself, you change the parameter just a little bit, can we guarantee or not that the dynamics are the same? So formally, that could be that the Julia sets are basically the same. So formally it really means the following, that if you perturb the parameter just a little bit, is the new dynamical system conjugate to the original one by a homeomorphic change of coordinates, a topological change of coordinates. So in other words, just doing a coordinate change is the dynamics exactly the same. And we can detect that in complex dynamics by a study of the periodic points. So we can take something that's topological or even analytic and turn it into something that's algebraic. And so the condition, one can think of it in terms of algebraic objects. So stability can be characterized as a condition where the periodic points, which are nice sort of algebraic curves living over your parameter space, you're parametrizing the points where it satisfies a relation. F, some iterate of a point z is equal to z. So the periodic points are defined by an algebraic condition. So you have these pieces of algebraic curves, and stability is where those pieces do not collide. Stability is where those pieces of algebraic curve do not collide. So failure of stability, in other words, bifurcations, take place when there's some periodic point that you can follow that crashes into another one at some parameter. So you have some condition defined by some iterate f of z equals z, so maybe it's a fixed point, and then you have some other periodic point, and if there's a collision between those algebraic curves, that is an obstruction to stability in the topological sense. And it turns out there's an equivalence here that one can analyze. Okay, so stability is where, so in other words, what you should picture, now remember, for any given map, you have infinitely many periodic points and pre-periodic points. And how are they organized? They're sitting inside some fractal subset. So stability means that fractal set itself is varying nicely as you move your parameter. And collisions interfere with that nice variation, so that even that fractal picture will fail to vary continuously. All right, so stability is where you have this nice picture, and they're all sort of fitting together in some kind of foliation of a subset of your space. By the way, I'm working in a setting where my parameter space is some algebraic curve. And so the failure of stability in the total space is in fact expected. It's known from work in the 1980s that on an open and dense subset of the parameter space, you have nice foliation type pictures, you have stability on an open and dense subset. But when you have an algebraic family like this, unless it's trivial, it turns out you will always have bifurcations. In fact, that is a theorem of Macmullen from the 1980s. This picture was for the quadratic family. The famous Mandelbrot set is a picture of where the bifurcations are taking place, where those collisions happen, viewed inside the parameter space. So if this is just a copy of the complex plane, that's my X here, so it's a picture in the base here, and the boundary of the Mandelbrot set is a sort of a projection of where, the closure of where those intersections take place. So, and one of the things that Macmullen proved in his thesis, in fact, was that whenever you have an algebraic family of this sort, you will always have bifurcations, except if the family is trivial, so maybe it's all just the same map, or it turns out in that special setting of lattice maps, where the family could be from varying the complex structure on the torus, there you do not have collisions at all, because you have a genuine foliations coming from the torsion points inside that family of tori. Okay, so you will always have these kinds of bifurcations. So one of the things, just to sort of cut towards the end, to say where I'm going with this, is that one of the things that Mirto and I were doing was to take this theory of bifurcations and sort of use it to build measures, in fact, on our parameter spaces that we can feed into some sort of machine related to arithmetic intersection and equidistribution statements that involve certain metrized line bundles on appropriate algebraic varieties. The key input is a positivity statement. One needs to know that certain top intersection numbers certain intersection numbers are positive, that you have some kind of bigness or nefness associated to your line bundles. And what we're going to do is use the complex stuff to feed in that needed positivity to run the equidistribution. So what I'm telling you here is where the positivity is coming from. I won't have time to tell you the whole rest of the proof or anything else, but just the input that we use from complex dynamics. So the next step I want to say, so there is this notion of okay, I haven't told you what positivity or what measures or anything else. There's just a notion of bifurcation that I've introduced. But one can take this one step further. The idea that when you have an algebraic family, there are always bifurcations. There are always going to be collisions somewhere. One can boost that to some sort of next step up, which is to say, not only are there collisions of the periodic points with themselves, but there will also be collisions with some ambient algebraic curve that you specify. So you have your family of dynamical systems, and you just throw down some other algebraic curve. For example, maybe it's a section over my x, it doesn't matter, but I have some point P that I'm thinking of that's moving. Then again, as long as the family is not trivial, or that this point happens to just be already one of the periodic points, you will necessarily have collisions with this P. So this is sort of a version of Macmillan's theorem, but like a relative version, or this ambient version, where you have this family of dynamical systems, I have this algebraic curve, and I should have drawn another picture. There has to be some periodic point that's going to cross my P. You can't just miss the P. You can't miss P. Unless it happens to be a piece already of one of these foliations itself. And so what do? So we sort of build this up to define a notion of stability that works well when studying pairs of maps, not just individual maps. And so we study what we call a pairwise stability theory, which builds on the regular complex dynamics theory, where let's say we have two maps, F and G. Maybe one of them happens to be, for my picture, I've decided to make one of them a family of lattice maps, where its periodic points really do fit together into a nice foliation, and the other is some messy foliation with lots of intersections and complicated behavior. But the point is, and what we study and what we prove is that these two sets of periodic points that are somehow independent are forced to cross over each other, and in fact to do so in a rather robust way, that you can actually get multiple intersections on single fibers is the goal, is the name of the game. So we introduce a concept of pairwise dynamical stability, which is where the periodic points for two different families, stability is where they don't collide, and then bifurcation, pairwise bifurcation, is where they do collide. And there are some settings in which this study already exists and is known. And this is related, by the way, just for the dynamics people in the room, I'm introducing this as a concept of two different families in dimension one, but really one should think of this as a family of dynamical systems in dimension two. In this case, it's just the product map, F and G. And so it's really studying higher dimensional complex dynamics and what happens in a family of higher dimensional dynamical systems. And so one should really think of this as just one case of a much broader problem of studying bifurcations in higher dimensional systems, which is an active area of research in complex dynamics right now. Okay. All right, so, okay, so just to say just a few more words. This was, again, just the slide showing the theorem. So just to remind you, what we were aiming for was the statement that if you fix the degrees of the maps, there's a uniform bound so that this intersection, even though the fractal intersection can get very, very complicated and the fractals can look more and more like one another, nevertheless, there's still a uniform bound on how many periodic or pre-periodic points the two maps can share over the entire space of all possible pairs, unless they happen to be the same. So that was the statement. So here was this overview of the proof, and the part that I was talking about was just a little piece of the input. So the setting, again, in our statement was that we have two algebraic families of maps, F and G on P1, that are parametrized by some quasi-projective complex algebraic variety. But if you assume that everything's defined over a number field, which we can because we were looking at the total space of all maps, which can be defined over Q, then we can take advantage of a lot of history and a lot of mathematics related to from arithmetic geometry and related areas. But in order to apply a lot of this machinery, the input, as I said, is some bigness concept. It's some positivity that one needs associated to some certain metrized line bundles. And so what we're really doing is using the complex dynamics for positivity. And just one more comment for the complex dynamics people in the room that I want to say. If you're familiar, so as I said, it was related to the bifurcation theory for higher dimensional dynamical systems. And so if you're familiar with, for example, the work of Matteo Astorg and Fabrizio Bianchi, who were studying bifurcations of families of maps on projective space in dimension 2. They were specifically looking at some skew product families, and they proved that something called the bifurcation current, if in their family is non-trivial, the support of that current is equal to the support of its higher wedge powers, in particular what's called the bifurcation measure. And from just a heuristic point of view, for the non-dynamics folks in the room, just so the bifurcation current is an analytic object that's detecting and even quantifying the bifurcations themselves. When does stability fail? So it just determines when does stability fail. The measure, which are those higher wedge powers, is detecting what we'll call strong bifurcations. So it's sort of a much like a real failure of bifurcation. So it's this top wedge power of that bifurcation current, sort of how much bifurcation is really happening. And in one-dimensional dynamics, the measure is much smaller than the current. I mean, it's a higher wedge power. The supports are not equal. But in that higher dimensional dynamical setting, one of the things they prove is that you can build examples where the supports are the same. So any type of bifurcation automatically leads to higher bifurcation and strong bifurcation. So from a conceptual point of view, it's reminding me of Scanlon's automatic uniformity in some sense. You have some statement, you get a finiteness statement, and if you're lucky, you also get an automatic uniform statement. And in this complex dynamics, we have some kind of bifurcation. And then if you're lucky, you get automatically strong bifurcation. And that's, we think now, actually typical in the higher dimensional complex setting. And it's not true in one-dimensional dynamics. But here we're actually secretly doing higher dimensional dynamics, even though I've formulated everything on P1. I have to remark, an alternate proof of the statement that I was discussing was recently obtained by my PhD student, Jitwoo Yap, in the setting, not for all maps on P1, but at least in the case of polynomials. And so we are all, so Mirto and Jitwoo and I are all discussing now how we can take some of his methods and combine them and see what else we can get. So before I finish, I just wanted to make a few more remarks. I'm glad I have a few extra minutes. So of course, I've been interested in this particular statement about pre-periodic points. I still don't know how big that intersection can be. I don't even quite know what techniques I should use get an explicit bound or to find examples that have the largest possible intersection. There are some examples known and some record holders known, but I feel like other techniques are going to be needed. The complex techniques might take us in one direction, but I think other techniques will be needed, which is one of the reasons I'm talking about it here. I'm hoping maybe some ingredients from model theory or other areas could be useful in these problems, just in the same way that they were useful in the Money-Mumford problem and other unlikely intersection problems, where the theory of O minimality has been particularly valuable. So I'm hoping that there will be a lot of techniques. I was working on a similar or related problem about 10 years ago, when I learned about the work of Zoe Chatzidakis for the first time. I know a number of you knew her well. I didn't. I only met her once or twice. And I was working on a problem related to, well, actually not so far away from the problems I've been talking about today, but related to the study of height functions, canonical height functions associated to dynamical systems in the setting of function fields. And she, together with Udi Hrushkovsky, had posted these papers, I guess at first in 2007. Anyways, these are version 2 from 2008 that were on the archive. And so since we're devoting Wednesday to her work and to celebrating her contributions in mathematics, I just wanted to mention that these are the work that when I was introduced to her work, and I sort of take this as an example of how these different fields of mathematics have come together in recent years and a lot, and especially with the dynamics and the model theory and algebra and all these different areas. And so I just want to take this as inspiration. I wanted to mention that. So to close, I want to go back to the picture that I showed you at the beginning of the talk. This Mandelbrot set picture, together with all these tangles of curves that you see coming around it, is the support of what we call the pairwise bifurcation measure for a particular example. And the particular example of pairs is where one of the families is constant and is just the z-squared family. And the other family is this famous family of quadratic polynomials, z-squared plus c. And the positivity of this, the fact that there is a measure, whatever that measure is, I have not given you the definition, but whatever that measure is, this is a picture of its support. The support includes the entire Mandelbrot set, including its interior, together with the union of these curves. And just the existence of that measure put into the machine tells us that there is a uniform bound, say m, on the number of roots of unity that can be pre-periodic for any quadratic polynomial, except for z-squared itself, in which case all of the roots of unity are pre-periodic for z-squared. But as long as c is not equal to 0, there's a uniform bound on the number of roots of unity that can be pre-periodic. Sorry, so I don't know why I put simultaneously. Cut out the simultaneously. That can be pre-periodic for a point GC. Sorry, remove that word. Doesn't make sense there. So this is the measure that gives rise. But I don't know what the properties of this measure are. I just know it exists, and here's a picture of it. And I had help from Caroline and Alex to draw this picture a few years ago, but I don't know a whole lot about this measure. And I think it's an interesting example to try to understand more. I also don't know what that number m can be. I don't know how big it can be. I mean, it's fairly easy to write down examples where m is at least 4, but or maybe even 8. But from certain symmetry considerations. But I don't know how many roots of unity a given polynomial that's not z-squared can have as pre-periodic points. I would love to have an explicit bound, and in the one setting where I know we can get effective results and give explicit numbers, it involved properties of the measures itself. So I would expect that perhaps by understanding some features of this measure, one might be able to spit out an explicit value, whatever that may be. Okay, so it's 10:21, so it's a good place to stop.